to be part of the equation.
Thank you very much. Welcome to Perimeter Institute here in Waterloo, Ontario, Canada. My name is Greg Dick. I'm the Director of Educational Outreach, and it is a pleasure to welcome everyone here this evening. And first, before we begin, in the spirit of understanding and learning from what has come before, Perimeter respectfully acknowledges that we are located on the traditional territory of the Attawandaron, the Anishinaabe, and the Haudenosaunee peoples. Perimeter is situated on the Haldimand Tract, promised to the Six Nations, which includes 6 miles on either side of the Grand River. And also, I would like to take this opportunity to thank BMO for Women for supporting tonight's lecture. So thank you very much, BMO. If you're watching online, you can join us on social media. We are at Perimeter and use hashtag #PILive. And if you'd like to, you can ask questions and be in conversation with our scientists behind their keyboards. And also, I'll take questions from the online feed for the Q&A at the end. And now, it is my pleasure to introduce tonight's very special guest speaker, Dr. Elizabeth Tasker. Dr. Tasker is an astrophysicist at the Japan Aerospace Exploration Agency. She received her PhD in computational astrophysics from the University of Oxford and was a Canadian Institute for Theoretical Astrophysics National Postdoctoral Fellow at McMaster University. Her research explores the formation of stars and planets using computer simulations. She's interested in how diverse planets might be and what different conditions might exist beyond our solar system. Dr. Tasker is also a keen science communicator and a writer for NASA's Nexus blog, the Many Worlds online column. And she has a popular science book called The Planet Factory, which was published last April. Tonight, Dr. Tasker will lead us through some of the alien worlds that we've discovered in our galaxy and ask the question, might someone else already call them home? Please join me in welcoming Dr. Tasker.
Thank you very much. Well, today I would like us to go on a tour beyond our own sun. But I'm going to start with a planetary system that I hope is rather more familiar. This, of course, is our solar system with the sun and surrounded by 8 planets, 4 rocky ones close to the sun, Mercury, Venus, our own Earth and Mars. And then beyond those, 4 gas giants, where the majority of the planet's volume is taken up by their colossal atmospheres, Jupiter, Saturn, Uranus, and Neptune. And until the early 1990s, these were all the planets that we knew about. It wasn't that we didn't think other stars would also have planetary systems, but it's just so hard to detect the tiny planet whisper around a bright star that it wasn't until only 25 years ago that we were able to sense their presence. However, since then, we have discovered over 4,000 planets beyond our star, and these are the extrasolar planets, the exoplanets. So if we take a brief demographic of what we find that approximately 5% of the worlds that we've discovered are huge planets, even larger than Jupiter. About 55% have radii larger than about twice that of the Earth, up to these mega Jupiters in size. And finally, 40% have radii less than twice that of our own planet. And it's this final population that causes us to ask a very important question. Could any of these worlds that we've discovered actually support life? Well, before we go any further, we're going to need to do a reality check. What do we actually know about the planets we've discovered outside our solar system? Now, it turns out that the vast majority of that 4,000 plus population were discovered with just 2 different methods. Approximately 20% were found using the radial velocity technique, sometimes called the Doppler wobble. Now, to understand this technique, let's first consider a planet orbiting a star. We normally consider the star to be basically stationary and the planet to be doing the legwork. But in fact, planets also exert a gravitational pull on that star. And this causes the star to do a small orbit of its own. And it's this motion, this wobble, that we detect and indicates to us there is a planet in that system. Now, the more massive the planet, the stronger it pulls on that star, and so the larger the wobble. So by measuring the size of the star's wobble, we get a feel for the mass of the planet. So what we find about the planet at the end of that technique is its orbit, but also its minimum mass. Now, you might say, why minimum? You just told me the star wobble is proportional to the planet's mass. And it is. The problem is we can't always see all of that wobbling motion. So for instance, if our planet is orbiting edge-on compared to our view from Earth, no problem. All of the star's wobble is towards us, and we see the whole thing. And this means that our measured mass of the planet is equal to its true mass. However, if we now tilt that orbit, what we find is that only part of the star's motion is towards us on Earth, whereas there is a bit more that we can't see. And as a result, we underestimate how much that star is moving due to the presence of the planet. And that causes us to underestimate the planet's gravity. So what we find is our measured mass is actually less than the true mass of the planet. Now, this technique has recently been in the news because one of the first planets ever discovered, and indeed the first one around a sun-like star, was found with this method. And this, of course, is 51 Pegasi b. Now, this was a very surprising discovery, because 51 Peg b is a planet similar in size to our Jupiter. Okay, no surprises there. But the planet isn't orbiting very distantly from its star. Jupiter takes about 12 years to loop the sun. 51 Pegasi b loops its star in a staggering 4 days. It's closer than Mercury is to our sun, and its distance between its star and the planet is only 5% of the distance between the Earth and our sun. And this discovery opened up the floodgates to really discovering many, many, many new exoplanets. And because of that, it was part of the Nobel Prize for Physics this year with Meyer and Queloz. Now, the second technique, which has discovered a staggering 75% of the planets that we know about, is the transit technique. And this is the technique used by our most famous and prolific planet hunters, the Kepler Space Telescope and its more recent follow-up, TESS. Now, in this method, the planet crosses in front of the star from our view of Earth. And as it does, there is a corresponding very small dip in starlight as the planet blocks out a little bit of that light. And the bigger the planet, the more light is blocked out. So this technique doesn't give us mass, rather it gives us the planet's radius. Now, if you're very lucky, you can detect the planet through both of these techniques, but it is difficult. For instance, many planets just don't transit their star compared to our view on Earth. So, for example, if you were to view our own solar system from another star, the probability that you would see the Earth transit across the star's surface is less than 0.5%. But if you're lucky enough to detect the planet with both techniques, then you get the minimum mass from the radial velocity, and you get the radius from the transit. Now, the transit also tells you what the inclination is on that orbit. So that means you can correct for the minimum mass and get the true mass of the planet. But nevertheless, this doesn't give us a whole lot of information about these new worlds. You typically have discovered it through radial velocity, and then you get a minimum mass, or you discover it through transit and you get a radius, or best case scenario, you see it through both, and you manage to get the true mass and the radius. But that's not a lot of information. It's only size. And the problem with that is actually rather obvious from our own solar system. If you only have size to go on, can you spot the twins? Rather than, fortunately, from the point of view of habitability, it's Venus and the Earth. These two planets have very similar radii and very, very similar masses. And indeed, before we'd actually visited the Venetian surface, we thought it may indeed harbour an environment quite similar to Earth. And I'm going to demonstrate that with a science fiction movie from 1965. And we all need to take a minute to appreciate how wonderful this is. So here, astronauts are going to descend to what they think the Venetian surface is going to be like. So first of all, we seem to have a kind of dinosaur, then maybe some more dinosaurs, and then lots of water, some plants that look like they eat people, some more dinosaurs, and then, yes, more death by dinosaurs and an octopus. So, maybe not very hospitable to us, but definitely habitable. And while this was a fun movie, the point that Venus could be a habitable environment was taken very seriously. And indeed, when the Russians launched Venera 4, Venera 4 was aiming to go to the Venetian surface. And they designed the spacecraft so that it could, if necessary, land on water. In fact, Venera 4 never made it to the Venetian surface. It burned up about 20 kilometers above that surface due to the extremely high temperatures and high pressures. However, Venera 13 and Venera 14 did make it down to the surface and sent back images. Neither survived longer than 2 hours. And at one point, I asked one of my colleagues, Kevin McGoldrick, who studies Venus, and I said, Kevin, I want to know what it's like on Venus. Could you describe it? And he said, no problem. He said, just imagine taking a hot plate and waiting till it goes cherry red. Now take your bare hand and press that down on that boiling hot plate. Now you have perhaps a slight sense of what it would be like to walk around in temperatures which average at 460 degrees C. But you still haven't got the whole picture because Venus has a thick atmosphere. So with your hand still on that hot plate, I want you to run it over by a truck. And then you'll get a feel of what it's like under 90 atmospheres of pressure. So Venus definitely isn't a habitable world, but here we are with two planets that are very similar in size, and that's really the only property we have for exoplanets. Now you might say, wait a minute. Venus and Earth do not have the same orbit. Venus is closer to the Sun. So can't we just say, okay, there's some sort of sweet spot at the Earth's position where it receives exactly the right amount of sunlight to have a surface that is not like being run over by a truck while holding onto a hot plate. So is this sort of a perfect temperature right here? And this is the idea behind what we call the habitable zone, the idea that orbit matters because most of the planet's energy is coming from the star. So here you have the idea that if you're too close to the star, you're going to be too hot. If you're too far away, everything is going to freeze. But there's sort of a middle ground where things are just about right for a nice bowl of porridge. And this is why this is called the habitable zone, or sometimes the Goldilocks zone for that reason. But, sorry guys, we need another reality check. Is the habitable zone indeed a zone in which planets are habitable? And I'm going to use our own solar system again to demonstrate a rather big flaw. So this is our sun's habitable zone. The Earth is inside it. Great, looking good so far. Venus outside it, again, very good. We're feeling confident. But of course, the moon is inside the habitable zone, and it doesn't have lakeside retreats. But you might say, well, it's the moon, I'm not going to count that. But you've got a bigger problem, because Mars is also inside the sun's habitable zone. Mars is definitely a planet, and while it may have been habitable in the past, I think we can't really say that its current landscape is what you would call habitable zone material. So why is this? Why doesn't this concept entirely work? So we have a region in which we think the Earth should be habitable, but we have these uninhabitable planets inside it. And actually, I can demonstrate this with an analogy that I feel everyone in this room is going to relate to, especially after today. So we have to picture that it's Canada in winter. See, I told you this was going to be easy. And you've decided in your generosity to pick up your friend from the airport. So you leave your apartment and you dress appropriately for the conditions. And you arrive at the airport and your friend steps off the plane, but they're dressed in a very light anorak. So they leave the airport and promptly die. And you're like, I'm really sorry this has happened, especially because I drove all the way to pick you up from Pearson. But my dude, you're not even wearing pants. And the point is that while you found conditions completely habitable because you were wearing the correct clothing, your friend would have found Canada completely uninhabitable due to the fact they were only wearing a light jacket. And similarly, the Earth is also wearing a jacket. More specifically, it's wearing its atmosphere. And its atmosphere controls how much sunlight it needs to have a temperate surface. So what this means is the quality of your jacket will depend on where you're most comfortable. So if you're wearing, a thick anorak, you might be good in this orbit. If you have a light jacket, you're going to need to be nearer the sun in order to stay warm. Likewise, if you have a very thick coat, you'll want to be further away or you're going to swelter. But here's the problem. For exoplanets, we can know the mass and the radius, but at the moment, it's very hard for us to know what kind of jackets those planets are wearing. So if we don't know what atmospheric coat they've got on, we actually don't know which orbits are going to be habitable for them. So what do we do? Because we often talk about the habitable zone when it comes to exoplanets. What we're really doing at that point is we're saying it's habitable for the Earth, wearing the Earth's atmosphere. So really the habitable zone in terms of exoplanets is the Earth's habitable zone. So what assumptions are we making? What atmospheric cloak do we have on? Well, when sunlight hits the Earth heats up and it emits in the infrared. And this radiation moves out from the Earth, but is actually absorbed by the gases in our atmosphere, in particular carbon dioxide, which trap the heat close to the planet and keep us warm. And this process is pretty much identical to what happens in a greenhouse, where the glass of the greenhouse lets the light in, but it traps the heat trying to come out. And this is why we call gases like carbon dioxide greenhouse gases. Now, the Earth has various different types of greenhouse gases, but for the habitable zone discussion, the one that's important is carbon dioxide. So, with our carbon dioxide greenhouse gas, the average temperature of the Earth is about 15 Celsius. If you were to strip away our atmosphere and just let the light come in and the infrared escape, our average temperature would be a rather chilly minus 18 Celsius. And our planet would be a snowball, and certainly no life that we know today would exist on it. And the point here is I haven't changed the Earth's orbit to turn it into a snowball. It's still in the habitable zone. I've just stripped it of its atmosphere. So you'll notice that the habitable zone has a certain width to it, within which I'm going to tell you the Earth is basically okay. And the reason for that is that our atmospheric jacket is adjustable. So we can pull back the hood, maybe unclip the fleece liner, and wear something slightly lighter. Alternatively, we can zip up and double up that fleece liner and get a slightly warmer atmospheric jacket. And the planet does this by adjusting the level of carbon dioxide in the atmosphere. And on Earth, that is controlled by something called the carbon silicate cycle, which I'm going to appropriately take a glass of water at this point. So carbon dioxide in the atmosphere dissolves in rainwater and falls down to our rocks, whereupon it reacts with those rocks and gets swept through our rivers and streams into the sea. After that, it forms a solid and becomes sediment in the planet. And eventually, that carbon is returned to the atmosphere through volcanic activity and completes that cycle. Now, this process here is what's key. If we zoom into this weathering process, we'll see that it is temperature dependent. So our rain falls onto our rocks. Now, if you increase the brightness of the sun, for instance, by walking a little closer to the inner edge of the habitable zone, you'll find that the precipitation will increase, and also the reaction rate with the ground will increase because chemical reactions occur faster in warmer weather. And that means carbon dioxide will be taken more rapidly out of the atmosphere, and will reduce the amount of greenhouse gases trapping our heat. So, in short, we'll put on a lighter jacket. Conversely, if we walk out to the outer edge of the habitable zone, then the reaction with the ground will slow down because it's cooler. And this will allow carbon dioxide to build up in our atmosphere. And so we effectively put on a warmer jacket. Now, this process isn't particularly quick. It takes millions or hundreds of thousands of years to sort itself out. But it is a way of making sure the Earth stays temperate throughout the habitable zone. So, if you take a planet in the habitable zone, what we're hoping is that it's roughly the same size as the Earth, and that it's wearing the Earth's atmospheric cloak of nitrogen, oxygen, and an adjustable amount of carbon dioxide. So if you push this planet close to the inner edge, then initially all is fine. We start losing carbon dioxide from the air, and we put on a lighter jacket. If you push that planet past the inner edge, things start to go a bit wrong. In particular, water starts to evaporate very rapidly. And as it goes into our upper atmosphere, radiation from the sun breaks apart the molecule into its constituent oxygen and hydrogen. The Earth's gravity is sufficient to hold on to the oxygen, but not sufficient to hold on to the hydrogen, which escapes into space. And through this mechanism, the planet just rapidly loses water until it becomes a dry and desolate landscape. Now, conversely, if we take our planet and push it outwards, initially all is fine. We put more carbon dioxide in the atmosphere, and we get a thicker coat on. But if we go outside the edge of the habitable zone, then the carbon dioxide itself begins to get so cold that it condenses into clouds. And the clouds reflect the sunlight that there is. So even the weak amount of sunlight that we're getting at that edge is just reflected away. So rather than keeping the planet warm, these carbon dioxide clouds make it even colder. And at that point, the planet freezes over and it's all over. So when we talk about the habitable zone, we're talking about the region in which the Earth can control its climate sufficiently to support surface liquid water. That means when you see a headline like this, we've found dozens of potentially habitable planets, what we're really saying is that we have measured the planet's size and found it approximately sized. And we have a habitable zone. Where with the potentially habitable is that that planet is decked out in a coat that's very similar to the Earth's atmosphere. And if those things prove to be true, then the planet might indeed be able to support liquid water, which would be good for habitability. So really, rather than saying potentially habitable planets, what we should say is Earth-sized planets that might be dressed in the right atmospheric coat for the conditions with an adjustable carbon dioxide liner. But for reasons I don't quite understand, I've never really been able to get this to catch on. So, if the habitable zone depends very strongly on the type of atmosphere the planet is wearing, and we don't know what kind of atmosphere that is, you might reasonably ask, is the habitable zone even useful as a concept? And the answer to that is yes, it is. Because it's true that if there is another Earth out there somewhere, we will find it in the habitable zone. So that means it's a way of sample selecting through these 4,000 plus planets to find the ones most likely to be Earth-like for future study. Now, of course, life may not be restricted to Earth-like planets. There's no reason why it couldn't be quite different. But it's going to be pretty hard to detect. And the truth of the matter is, we're most likely to be able to successfully detect life if it is at least somewhat like our own. So one solution to this might be to rename the habitable zone, something more clued in to what it actually is. So a name I've used in the past is temperate zone. I use it in my book and I've used it in a few research papers. And I like the fact you're no longer saying the word habitable, because I feel that's a very loaded term where everyone has expectations about what it means. But in truth, the habitable zone is still only temperate if you're wearing the right atmospheric coat. Mars isn't remotely temperate. So maybe we could say, well, how about hunting zone? Because it's really the zone in which we hunt for other Earths. But that has some slightly negative... So one solution to this was suggested by Jessie Christensen at NASA, and she suggested the Ecclewatts zone. And this stands for Earth could have liquid water on the surface. It is brilliantly accurate, but as she put when she put this on Twitter, it's not very pithy, is it? And so I was saying, but Jessie, I love it. You know, it's accurate, it tells you what's going on. And Chris Lindott from Oxford said, no problem, we can solve this. We'll tell everyone it's actually the name of an obscure river god. And maybe they'll sort of embrace it as, oh, do you remember the god Ecclewatts? Oh, yes, definitely. Now, of course, all these problems would be solved if we could actually detect the atmospheric coats. And if we're ever going to talk seriously about habitability, this is what we're going to need to do. So, fortunately, we're right on the brink of being able to do that for a lot of planets. The idea here is as the planet transits across the star, some of its light will pass through the planet's atmosphere. And as it does, it will hit molecules in that atmosphere, and some very specific wavelengths will be absorbed. So if you know what wavelengths are absorbed, and you know what molecules do the absorbing, you can work out what atoms are in that planet's atmosphere. Let's take another look at that. So at the moment, we have the planet transiting across the star, and we measure its radius based on the light that's blocked by the planet itself. Now, supposing that planet has an atmosphere, and you can see that some of that starlight is passing through the planet's atmosphere. And as it does, it's going to meet whatever molecules are in that atmosphere. Now, let's just pick a particular molecule that's going to be blue and yellow. So this particular molecule doesn't give anything about blue light. It doesn't care about it, it just passes right through. So as a result, if you looked at the transit in blue wavelengths, you would still measure the same radius for the planet, only the planet itself is blocking out that light. But this particular molecule is going to find red light particularly delicious. And it's just going to absorb all those wavelengths. So it means if we have our telescope here, we don't see any light coming not just from the planet's solid surface, but also none of it passes through the atmosphere. So we end up measuring a bigger radius at those wavelengths because they've been munched up by the molecules. So if we have an instrument that's capable of looking at lots of different wavelengths as the planet transits, then we can see when the atmosphere starts blocking certain wavelengths. And this can tell us what molecules are there doing the absorbing. So one of the projects I'm really excited about that's coming up is the European Space Agency's aerial mission. And this is capable of doing exactly that. It's going to look at these transits in lots of different wavelengths. And it's going to do a big survey. So it's going to look at nearly 1,000 planets, or maybe even more than 1,000 planets, and 500 of these in more detail. But it isn't going to launch until 2028, which is a bit of a wait, and really, who's got any patience nowadays? No. Fortunately, literally no one has any patience. And so we have been able to do a little bit of this atmospheric sniffing with our existing instruments, in particular with the Hubble Space Telescope. Now, I want to take a minute to acknowledge that Hubble was launched in 1990. Before we discovered any exoplanets whatsoever. And now we're using the same telescope not just to find these planets, but to actually look at their atmospheres. That's kind of incredible, isn't it? So recently, Hubble looked at the atmosphere of a particular planet and made a discovery that splashed all across the news. And this was the planet K2-18b. And what Hubble saw was that this planet had water vapor in its atmosphere. And the planet orbits within the habitable zone. And this got many, many people really very excited. So we had headlines like this: water found for the first time on potentially habitable planet, from the BBC. And in fact, this was echoed by absolutely everybody. And some of these headlines are frankly quite entertaining. Some of my favorites were The Guardian: water found on the most habitable known world beyond our solar system. What does that even mean? We only know of one habitable planet. Or we have from The Times: Earth-like planet has water and climate to host life. Do you think we might have jumped the gun a little bit here? And we have from the Japan Times: water discovered on first time on a habitable exoplanet. Let's just scrap potential. We have a habitable planet. And this was an incredible discovery. I do not mean to downplay it in the slightest. But I'm going to give us our third reality check. And I'm going to ask, what do we actually know about K2-18b? So first of all, this planet has been detected by both the radial velocity and the transit technique. So we have both a mass and a radius. And the planet weighs in at 8 Earth masses, so it's quite a bit larger than us. And its radius is about 2.3 times that of the Earth. Now, combining those, we can have the mass and the volume, and that gives the density. And the density of K2-18b is 3.3 grams per centimetre cubed. Now, looking at this at first might look kind of promising. Mars actually has a very similar density, and Mars is a rocky planet. But here's the catch. As rocky planets get larger, their gravity gets stronger, so they're going to compress that rock more. So we expect larger rocky worlds to have higher densities. So, for example, the Earth has a density of 5.5 grams per centimetre cubed. If we kept the composition identical to the Earth, but scaled it up to the size of K2-18b, I believe its density would be around 10 grams per centimetre cubed, not 3.3. So what is in this planet that is able to give it such a light density? There are a couple of options. What we need to do is mix the rock with something else. Now, when Hubble saw the water vapor, it turned out the data is best fitted by adding hydrogen and helium to that atmosphere. This is not surprising. Hydrogen and helium are the two of the most common elements in the whole universe. And indeed, when our Earth was young, its first atmosphere probably had hydrogen and helium in it. But because our gravity is relatively weak, these very light gases would have escaped and lost from our atmosphere. But K2-18b has a bit more of a punch, and it could hold on to those light gases. Now, this gives us a bit of a problem when it comes to habitability, because if we assume that K2-18b is an otherwise entirely Earth-like, but has some hydrogen and helium, it's a bit like giving the Earth a very thick extra jacket, because hydrogen, like carbon dioxide, is a greenhouse gas, and unfortunately, it's a very good one. So, to get a density of 3.3 grams per centimetre cubed, you need to add in, I think, about 0.7% of the mass in hydrogen and helium. That doesn't seem like very much, but remember, these are light gases, so a little bit equates to a very big volume. And research done by Lopez and Fortney suggests that even if you have 0.5% of mass in these light gases, you end up with surface pressures greater than 20 times that at the bottom of the Mariana Trench, the most deepest point in our oceans. And the temperature on that surface would exceed thousands of degrees C. So you could have a planet in the habitable zone where the Earth would be perfectly temperate with some nice seas, but you could end up with temperatures that are in no way commensurate with liquid water. And indeed, biology might have a hard time at this point, because not only do you not have water, but the temperatures are so high, it's going to be quite hard to form molecular bonds. So, what does that mean? Is it all over for K2-18b, and it's just definitely not habitable? Well, there are some other options. Remember, all we've got to do is match that low density. Now, if we don't want to put too much hydrogen and helium in, because it's like wearing an extra coat, what other light element could we put in that would balance out the rock? Well, we've discovered water in the atmosphere. How about if we add a bit more water? By which I mean a lot more water. So to match the density of 3.3 grams per centimetre cubed, you need to make the planet about 50% water by mass. Now, we think of the Earth as a pretty water-rich planet because over 70% of our surface is covered by oceans. But in truth, by mass, the Earth has only less than 0.1% of its mass in water. So this is a huge amount more water. And such a world would be what we would call a water world. There's a beautiful animation done by NASA here, where we're going to zoom in and go through the clouds and get a feel for what that might look like. Now, in a water world, you would have no exposed land at all. You would just have fathom-deep oceans. So just water everywhere. But we do have evidence that such water worlds may indeed be quite common in the galaxy, because this isn't the first planet we've discovered with an in-between density. In fact, a few years ago, a very impressive discovery was made of 7 Earth-like worlds around the red dwarf star, TRAPPIST-1. And these are all roughly Earth-sized, and their density is all somewhat in between that of a rocky world and a gas giant, suggesting they also have a lighter element mixed in. But they're too small to be holding on to hydrogen and helium, so there's a fair chance it could be water. And 4 of these worlds exist inside the habitable zone. So this leads to the question, could a water world in a habitable zone actually be habitable? Well, there are some problems, you'll be astonished to hear. Again, on the surface, it seems like it should be no problem. NASA's mandate for astrobiology is follow the water. And that's because all life that we know on Earth needs water. Water is a fantastic solvent. It's really great for biochemistry. So if you find another place with liquid water, it's got a lot of the key ingredients for life. But as with most things, especially so close to Halloween, it turns out you can have too much of a good thing, be it candy or water. And the problem we have here is with our carbon silicate cycle. Now, if you remember, we were using the carbon silicate cycle to keep temperate within the habitable zone. You know, if we were at the inner edge, then the reaction with the rock was a bit faster. We drew carbon dioxide out of our atmosphere and cooled down. And conversely, if we were on the outer edge, then we could leave carbon dioxide to grow in our atmosphere and give us a thicker coat. But what happens if you cover the surface with water entirely? Can you still get any kind of weathering? And the answer is it depends on the depth of that ocean. If the ocean is shallow enough, you can get some sort of weak weathering with the ocean floor, but it's kind of a poor approximation, partly because the ocean temperature doesn't directly reflect the air temperature. So it's a bit like a wonky thermostat. And if it doesn't change properly with the planet's position, what that might mean is your habitable zone shrinks and becomes a very narrow band, meaning that you basically have to be sitting bang on the right spot for temperate conditions, because you haven't got any wiggle room anymore if you can't effectively control the carbon dioxide abundance in your atmosphere. And this gives us some problems because every star changes brightness during its time. So back in the Earth's early days, the sun was a lot dimmer, and the Earth, if it had today's atmosphere, should have become a snowball. But in fact, we have evidence that the Earth supported life during that time. And one of the possible reasons is that our carbon silicate cycle was able to eject enough carbon dioxide into the atmosphere to give us a thicker coat and therefore keep warm during the sun's early days. If you can't do that, you have a lot less time for life to develop on the planet. because you can only do your life development when the star is bang on perfect for your position. So the second problem with this is that as the carbon is cycled through the planet, it also cycles the nutrients needed for life, such as phosphorus. So if you're not doing all that much in the way of cycling, you may end up with a lot less nutrients for generating life on the planet. So that might still mean you do get some life, but maybe it's a bit simplistic. And that would also mean that if the life wasn't a lot on the planet, we might not be able to detect it. So we don't just want life on a planet, we want detectable life on a planet. Otherwise, as far as we're concerned, the planet is uninhabitable. Now, if your ocean becomes deeper, your problems get worse. So in the case of K218b, if it really was 50% ocean, we would expect the pressure at the bottom of that ocean to be so high that you would form these deep sea ices. And these ices completely seal off the land from the sea, and they break your thermostat entirely. So at that point, you can't have any weathering taking your carbon dioxide out of the atmosphere. And indeed, with enough pressure, you shut off volcanism. So the planet becomes geologically dead. So that's not looking too good for life. So does that mean it's a definite no-no? Well, it doesn't, but we're going to go very theoretical at this point, because our own solar system has no water world, at least not surface water world, for us to explore. But some theoretical models have suggested that alternatives exist to the carbon silicate cycle, because all we really need in a habitable zone is a way of varying that carbon dioxide. It doesn't really matter how we do it. So one such model was developed by Levy and Ramirez, and they suggested that if you have a planet with ice caps and a thick carbon dioxide atmosphere, then carbon dioxide could actually become incorporated into the ice. And then these ices would eventually cycle through the planet, and the carbon dioxide would be released again in the warm equator region. And this would form a similar cycle to the carbon silicate cycle. There are a couple of small print catches to this. One is, for this mechanism to work well, then the carbon dioxide atmosphere has to be pretty thick. And that means you have to be on the outer edge of the habitable zone. Now, K218b isn't. It's actually in a similar position to the Earth near the inner edge. So if it had the required carbon dioxide atmosphere, it might be too warm in its current orbit. However, the creation of models like this tells us there might be geological processes that the Earth doesn't have that might rescue some of our exoplanets. Now, the second thing you need to know about this model is it requires the planet to have a very fast rotation rate, and that's in order to keep the poles cold and the equator hot. If you don't have that, the thick carbon dioxide atmosphere does a really good job of evening out the whole temperature. And this turns out to be a problem for the TRAPPIST-1 worlds because they orbit a red dwarf star. And you might think, why does it matter to the rotation rate what star they orbit? And the reason is that red dwarf stars are super dim. TRAPPIST-1 only has about 1,000th of the luminosity compared to the Sun. So its habitable zone, because it's so dim, sits very, very close to the star. So the planets in TRAPPIST-1 that are in the habitable zone, the one furthest out, has an orbital time of 9 days. So it does 1 year on this planet in just over an Earth week. Then the next one has 6 days for an orbit, 4 days, and 2.4 days. One long weekend on Earth does an entire year on the innermost world of the habitable zone on TRAPPIST-1. Starry, and it's much smaller than the Sun. The proximity these planets have to the star means that the star's gravitational pull on that planet is much stronger than the Sun's gravitational pull on Earth. And this causes the planet to distort. This is grossly exaggerated, but you do get a slight bulge in the direction of the star. So as the planet tries to rotate around the star, the gravity of the star pulls on that bulge, and it forces the planet to always face in the same direction as it orbits. So 1 day becomes 1 year at all times on these planets. And we call this tidal lock. And it's the same mechanism that keeps the moon always facing the same direction to the Earth. So as a result, while these orbits are very short, their days are very long. But if we say, well, okay, maybe this particular mechanism wouldn't work for controlling carbon dioxide levels, but possibly we could come up with another one, and therefore these worlds might still have some form of life. What would it be like on a tidally locked world? Well, a tidally locked world is a world of two halves. One hemisphere has eternal day, where the sun never sets. And the other hemisphere, it is forever night. And this means that the temperatures may be boiling on one side and then freezing on the other. However, if again we put an atmosphere on that planet, the atmosphere is a movable gas, and it can help redistribute that heat around the planet a little bit. So if the sun side gets very warm, that gas is going to get hot, it's going to increase in pressure, and then it can push round to the cold side and save it from completely freezing over. That's also true if the TRAPPIST-1 worlds turn out to be water worlds, because the water is also another movable fluid that can help move that heat around. So models suggest the result might be something like this, which we call eyeball worlds, where we have a melted ocean on the sun side, and then we freeze into snow, but not complete collapse on the reverse night side. And if you were to live on such a planet, possibly around the rim would be the best area between the snow and the water. And if you were to live there, you would live in a land of perpetual twilight, where the sun never rose and never set, but always just sat right there on the horizon. Now, until now, we have talked about habitable zones when there's just one star. But in fact, 50% of the stars in our galaxy have a twin, and they're in binary systems. So what happens to a planet if you throw another star into the mix? Well, let's assume that those stars are pretty close together. So, for instance, the difference between the sun and the Earth, let's replace the Earth with another star and let the planet loop around both of them. And we call this a circumbinary orbit. Now, when we have just one star, as you can see, we have a very symmetrical distribution, as you'd expect for the habitable zone. If the two stars are equal mass, that nice sphere becomes like a squashed capsule, because both those stars are emitting sunlight. If the stars are different masses, then you might have a system where it's almost spherical, but there's a bump here due to the weaker starlight from the second star. Now, you might look at these and say, well, they're a bit odd-shaped, but I think I could see a good orbit, sort of around here, or maybe like this. It could all be okay. I could stay very comfortable in this system. And you might be right, but you do have to allow for one more thing. And that is, these stars are not stationary with respect to the planets. They're going to be moving. So that means even if your planet is on a perfectly circular orbit, the amount of radiation it receives from its stars is going to change over that orbit. So if, for instance, it was orbiting near the edge of the habitable zone, you might find the planet slid in and out of the habitable zone over its year, causing some rather crazy climate things to happen. And indeed, we found a planet that might be doing just that. This is Kepler 16b, and it was discovered in 2011, and it's often called the Tatooine planet on Star Wars for very obvious reasons. Now, in fact, the NASA posters are very beautiful, but they have drawn this as a rocky planet, but it isn't. It's got a mass of roughly 100 times that of the Earth, making it close to Saturn in size and mass. But it does orbit in the habitable zone of its star, and the habitable zone looks like this due to the twin stars in the sky. And if you model what that looks like, you get something like this. So here are two black circles, are our two star orbits. The green is the habitable zone, and that blue line there is the planet's orbit, and you can see it ducks in and out during its time. And if you look for what happens to the radiation over that time, you can see that the temperature change be received by the planet varies by 15 degrees several times during one orbit. Now you might say, yeah, but come on. The difference between winter and summer is more than that. This doesn't seem like such a big deal. But what you have to remember is this is global change, not local change. And to give you an idea of how much difference that would make, during the Little Ice Age in the 1600s, the Thames in the UK and London froze solid. And we think that during that time, the global temperature of the Earth was dropped by 1 to 2 degrees. So if you imagined a 15-degree change multiple times during the year, that is some serious climate action. So could life survive this? Well, fortunately, we don't have to find out. But it would be interesting to know whether planets like this stand any chance of being habitable. And research suggests it is possible. If the average amount of starlight is roughly what you need for temperate conditions, then maybe life could just hibernate during those very inhospitable times. So in that case, in Star Wars' Tatooine, you might find that, the Force will awaken in 6 months. So what we've really covered here is a how-to of how to die horrifyingly while you're inside the habitable zone. So we've seen planets that are just wearing the wrong outfit for the occasion. They've either got too light a coat for the amount of radiation that's coming, or they're wearing too heavy a coat and they're getting too hot. Or maybe they're water worlds and we're just not sure whether we can cycle that carbon dioxide through the planet or not. Or alternatively, maybe they're locked in tidal lock and we get this eyeball situation. Or possibly there's 2 suns in the sky, and that just makes it harder to maintain a sensible climate. But for me, these are the planets I'm most interested in, because they're like nothing we've got in our own solar system. And by studying them, we're going to see geology and maybe even different forms of life, but different planetary conditions far beyond anything we've seen before. And I find that really exciting. After all, when it comes to Earth 2.0, well, we've already got one. So I just want to finish off with some fun things, just in case this just wasn't enough planets for you. So if you want to build a planet, strangely enough, I have an app for that. And I have some cards to give out afterwards if you can't remember the website address. But you can deal with this app either through the Twitter bot or on the website. And you take a planet just like ours, and we're going to change 3 tiny things that seem kind of insignificant. We're going to change the land fraction, so the amount of land versus sea on the surface, the volcano rate compared to Earth, and where in the habitable zone you sit. Are you right up the inner edge or closer to the outer edge? And you can see what types of surface temperature you can get from this. And then a neural network will generate you what the planet might look like. And what you can take away from this is you can have an incredibly Earth-like planet that is nothing like the Earth today. So just imagine how diverse the exoplanets in our galaxy really could be. Secondly, if you've been feeling a bit cheated by all this talk about habitable planets in the news, and I've just told you the habitable zone largely doesn't mean very much, maybe you'd enjoy looking at the Many Worlds column. This is sponsored by the NASA Nexus initiative, and it goes for in-depth stories on exoplanet and astrobiology. And I contribute a story roughly once a month or so, and the main writer and creator is Mark Kaufman, who was a NASA correspondent for the Washington Post for several decades. Finally, or not quite finally, this is good fun. So Ria Voris is a Canadian author. She lives in Victoria, and a few years ago, I suddenly got an email from her, and she was like, Elizabeth, I'm writing a book, and it's got a girl called Grace, and she's really interested in exoplanets. And the book isn't really about science, it's about how Grace's mother goes missing. But I'd like her to meet a real scientist. Could she meet you? And I was like, hell yes. So I am a character in this book. And I give Grace some very sage and slightly cynical career advice at several points during the volume. And finally, a shameless plug for my own book. If I haven't demonstrated enough ways to die on exoplanets, I can assure you I can demonstrate a lot more in this volume, where we have some truly dastardly worlds, from hot Jupiters to more Tatooines with multiple stars, to rogue worlds that have no star, to planets of seas or lava and tar. Really, there's no limit to the ways you could die horribly off this planet. Thank you very much.
All right, so if there's questions in the house, the microphone is there. You can form a queue, and while you're making your way to the microphone, we'll go to the online questions.
Okay.
And we have a few. Let's start with this one. It seems like the presence of magnetic field is necessary to keep an atmosphere. Are there any tools we have or will develop to measure the presence of exoplanet magnetic fields?
Right, so magnetic field is a bit of a pro and a con. We do think it does protect the atmosphere, and therefore it may be an important part of planet habitability. But detecting it around an exoplanet is incredibly hard. What we can do is we can estimate the rate of atmospheric loss without a magnetic field. And we have some really good data from NASA's MARVIN probe around Mars, which has looked at how solar activity strips away Mars's atmosphere. So I would say, at the very least, we can tell you if the atmosphere is still there after a period of time, it would be an indication that there was a magnetic field there. I'm not sure at the moment there's anything upcoming that could do better.
Thank you. Let's go inside the theater.
So you talked about the planet that we found near a Sol-like star, the hot gas giant. What kind of factors would be in effect if the planet was around a not Sol-like star, like not a G-type star, but like an F-type star or a K-type star?
So do you mean in terms of formation or conditions or?
Possibility for life.
So, I mean, the TRAPPIST-1 system is orbiting a red dwarf, and a lot of the smaller planets we've seen are orbiting these smaller, non-solar-like stars. And one of the reasons they're good is that because the star is smaller, the influence of the planet is easier to detect. So a lot of focus for future habitability has been on these worlds. But, basically every question is going to have a but. So the but with M dwarfs is, while they seem very dim and quiet and quite peaceful, it turns out they have a particularly rambunctious history. And before they hit what we call the main sequence, which is their main lifetime, they are immensely active, full of flares, and very hot. So it's possible that if you were a planet deciding to form around a red dwarf, before you'd really got on with your life, you might have been completely sterilized by all the radiation pouring off that red dwarf. We don't know if that's true, and there are things that could save you. So, for example, the TRAPPIST-1s are around a red dwarf, and so is Proxima Centauri b, which is our nearest exoplanet. And if they formed in their current orbit, it doesn't look too good. But maybe they formed further out. So you mentioned 51 Pegasi b. So one of the first questions people had about that planet was, how do you get a Jupiter that sits closer than Mercury? And the general answer is, we believe these planets formed further out, where there's more building material to make planets, and then they migrate in. Now, if that happened to the TRAPPIST-1 worlds or Proxima Centauri b, it might have been able to stay back from the violent red dwarf until it calmed down a bit, and then slowly saunter inwards. And if that happened, there's a chance. Does that help?
Yeah, thank you.
I can also tell you about one where there's really no chance for life at all, but it's really exciting. So the first confirmed planet we found was around a pulsar. And pulsars are dead stars. So they are stars that are larger than our sun that have become neutron stars, and they spin very fast and emit horrifying levels of radiation. But we actually discovered the first exoplanets ever with 2 planets around such a system. So that's incredibly exotic, but I would not like to live there.
Thank you.
Let's go inside the theater for another.
If you had a quantum leap in propulsion and you take the evolution a step further,
Let's do it.
Alpha Centauri, it's much older than the sun, but Proxima Centauri B, there is a planet there, but it faces the star one way, as you said, with TRAPPIST. So if you assume life maybe evolved but isn't quite, even though it's older, it's the age of steam, and we have this propulsion that can get there, whether it's negative energy or something less, the light sails. Is it wise to observe something like the prime directive of Star Trek, that we see something, it isn't as advanced as us, but what do we do?
So the question is, if we thought there was going to be life, do we go and give it a poke, or is that a bad idea? And yeah, I think there are different schools of thought on this. One of the things that we're developing now, of course, is remote observation. And if you take us into the future, that's going to get better and better and better. So I would hope that by the time we could even contemplate traveling to an exoplanet, which I think really would take generational ships where people have to live and die on a spaceship, we would have got really good data about that planet, and we would have been able to see whether it's habitable and maybe even had some level of communication. So I like to think we wouldn't go in blind unless we were so desperate we had to leave the Earth now and we went for it.
Is it reasonable to think that more advanced ones might be doing the same with us?
Well, they haven't said anything. So we do have the Fermi paradox to contend with. Like, if there are more advanced civilizations out there, where are they? And there could be lots of answers to that. There could be that actually complex life is super rare and you reach a bottleneck that could be called Brexit, for example. And then just, life disappears. Or, maybe maybe it's just too far away for us ever to really make contact with it. I think these are very hypotheticals, and I would want to know more before making really a decision.
Inside the theater one more time.
The good news is that we have 4,000 potentially habitable planets.
Whoa, we have 4,000 planets. Let's go with that.
Okay. Are we at the stage where we say a reality check of those 4,000, only 1,000 fall into that category? That we can discard 3,000?
We can discard everything except 24 of them.
Everything except 24.
So there are 24 planets that have sizes that suggest they should be rocky and are inside the habitable zone. A lot of that 4,000 are planets like Jupiter. And, I don't want to put limits on what life can do, but they're not good bets. Jupiter has really strong atmospheric currents which would throw bits of its gas up through extreme pressures and cycle regularly. That's not going to be good for developing long, complex molecules that life is likely to need. So if you assume that life really can't do a gas giant, which I think is reasonable, then you're looking at rocky surfaces, and you don't want too thick an atmosphere, so therefore the habitable zone is at least a good start, and we have 24 of those.
And do you focus now on those 24?
Yeah, exactly.
Thank you.
And of course, there may be life outside those. In our own solar system, we have a mission going to Europa. Europa is not in the habitable zone. It's really cold, guys. And it's full of radiation, but it may have life underneath its ice. But even if it did, for Europa, great, we could go there and explore it. But we would never be able to detect that life around another star. So those sorts of worlds aren't really that interesting to us if they're not in our solar system, because we can never detect the life if it's hidden from us. Yeah.
I'll go one online, and then we'll come back inside the theater. If we were on an alien exoplanet, a scientist on an alien exoplanet,
Yes.
and we're looking at Earth, what would we see? For example, does the Earth orbit affect the sun with the same kind of wobble that we would see in other planets?
So it does, but obviously not very much. The biggest problem we would have is that the probability of the Earth transiting the sun is very low. You have to be really lined up perfectly. And that's because the Earth is small and it's relatively distant from the sun. So to get that perfect alignment is quite rare. I think the probability is about 0.46% or something like that. So if you were on an alien world, there's quite a high chance you couldn't spot the transit of the Earth. You might be able to spot the wobble if you had very sensitive equipment. You would probably spot Jupiter's wobble, the wobble from Jupiter. And if you were able to build telescopes equivalent to LUVOIR, which is the successor for JWST that's been proposed, then you might even be able to get direct imaging. But it just depends on how big their telescopes are.
Thank you. Inside.
So my question is, it's about one Kepler and precisely, but also about other Keplers. So if we were able to make some sort of device that was able to reach Kepler 452b, which is my planet precisely, what would be our odds of being able to survive on that planet? And
You're going to have to remind me what Kepler 452b is, because I'm not that great at remembering all the numbers.
Oh, it's a planet that was discovered. It's a Kepler that was discovered in 2015, and its average temperature is 8 degrees, I think. Anyways.
Okay, so firstly, its average temperature is not what you've just quoted, because we do not know its atmosphere. What you have quoted is the equilibrium temperature. That is the temperature at the top of the atmosphere, and it is how we judge whether these planets are interesting or not. Now, if that has an Earth-like atmosphere, it might very well be temperate on the surface, but we have no way of knowing that. So as a result, I can't give you a probability that the surface would be habitable. We know it might receive the same amount of starlight as the Earth, good start. But unless it has a similar atmosphere to ours, it might have a Venetian-like surface down there. So until we can look at its atmosphere, there's no way of saying more about its habitability.
Right, so if we were able to reach the surface and live on there, would we be able to somehow change our odds of survivability in any way?
So you mean if we went down there and we had to make something like Venus habitable?
Yeah.
I never say never, but I wouldn't really like our chances very much. I mean, if you imagine what it would take to, resculpt Venus or Mars, it has been the subject of science fiction studies, and people have seriously considered it. But it's certainly well beyond any technology we've currently developed. And also the time needed to do it would be huge. So if you wanted to visit a planet, you would have to wait probably generations in order to do anything with it, even with far more advanced technology than what we currently have. So, I mean, never say never, but I don't think I'd be volunteering for that crew.
One more inside the theater.
Hi.
Hey.
Thanks for the amazing talk, by the way. Are there any other techniques, either in the works or maybe future techniques that you might be aware of other than the transit or the wobble?
Absolutely, that last 5% is what you're asking about. So there are a few. One of them is called gravitational microlensing. And the WFIRST telescope will be doing quite a lot of that. And what that does is it relies on a background star, and you see its light being bent by something dark and mysterious that you can't see. And that could be a planet. And that can give you the mass. Possibly, though, the most exciting thing in the works is direct imaging, actually looking at that planet directly. And we have done it. We do have examples. At the moment, the planets we're seeing, you will not be surprised to hear, are very far from their star, because starlight is very bright. So if you want to see the planet, you need to block out that starlight. So you can do that, but it then helps if the planet is quite a long way back. It also helps if the planet is a gas giant and young, because they emit the most heat. But our techniques are steadily improving. This technique is still in its infancy. So if we talk about the potential of LUVOIR again, for example, the pseudo-simulations that have been suggested for such a telescope actually reveal the Earth and Venus in direct imaging, which would be, it'd be astounding. And more than that, you get a lot more information from a direct image. Like, you might not be able to see mountains and seas. You've got 1 pixel per planet. But for instance, supposing you looked at that pixel over time and saw that it changed in brightness, that might be an indication the planet's rotating and you're seeing the difference between continents and seas and things like that. So like the whole idea of the transit spectroscopy, which is the light passing through the atmosphere, direct imaging can start to tell us what's really going on that surface.
Thank you.
Ladies and gentlemen, Dr. Elizabeth Taft.